All right, I'm going to be showing you a concept called ionic bonding. And there's a little bit of information that goes into it before we can start the actual practice of ionic bonding. This is a copy of the periodic table, and I'm going to be relying on this information that I have written up here. So it says 1 VE, 2 VE, and then I have +1, +2, and then over here on this side of the periodic table, it continues on. And then there's also charges here. The letters VE stand for valence electron. So what happens in atoms is they have an unstable number of valence electrons. I'll show you lithium as an example. So lithium has 3 protons, 3 neutrons, and 3 electrons. And I know that because it's number 3 on the periodic table. So that number right there tells you how many protons it has, and in an atom, everything is equal. Protons, neutrons, electrons. Protons and neutrons exist in the nucleus, so I'm just going to do that. And then the electrons exist in rings, or technically it's an electron cloud, but we're going to draw it as rings. So the rule is that you can only have a certain number of electrons in each ring. So the rule is that you can have 2 electrons in the first ring. You can have up to 8 electrons in the second ring and 8 electrons in the third ring. You can have more rings than 3. It's just that the rules kind of get a little wonky, and so we're going to leave it at the first 3 rings. How do you know how many rings to draw? Well, it depends on what row you're in. So rows go across, and because lithium is in the second row, I drew 1, 2 rings. If I was working with sodium, sodium is in the third row, so I would have drawn 3 rings. Okay, so the rule states that I can have 2 electrons in my first ring. 1, 2. Just put them anywhere on the ring. Those represent electrons. Well, lithium has a total of 3 electrons. So if I can only put 2 electrons in the first ring, that must mean that the third electron is going to go in the next ring. All right, so there's what lithium looks like in our model. Well, according to something called the octet rule, all, and I mean all, atoms want to have a full valence shell. The valence shell, also known as valence electrons, is the last shell. So this is the valence. Okay, so whatever is the last one. Okay, well that kind of goes back up here. Well, in the first ring, we'll call them shells or rings, whichever, can only have 2 electrons. So technically this first ring or shell is full. The valence shell is full. Well, I need to have 8 electrons, which is why it's called the octet rule, in this next ring or shell, but I only have 1. So that's a bummer. So lithium is considered to be unstable as far as electrons go because it does not have a full valence shell with 8 electrons. Okay, so that's half of the piece of the puzzle. All right, so what's going to happen is whenever an element or atom doesn't have a full valence shell, it's going to undergo the process of bonding. So bonding, ionic bonding, occurs when an element either gives or takes valence electrons from another element to complete the octet rule. And I'll show you what that looks like. So that's our definition. So we can either give away electrons or we can take valence electrons to complete the outer shell. So another example, another element, let's say fluorine. Fluorine is number 9 on the periodic table, and it happens to also be in row 2. So I'll draw fluorine down here. Fluorine is F, so if fluorine's number 9, that means it has 9 protons, 9 neutrons, 9 electrons, so that's its kind of profile. Okay, so then the 9 protons, 9 neutrons are in the nucleus. And because it is in the second row on the periodic table, I'm going to draw 2 rings. 1, 2. Sorry, I'm not very good at drawing rings. Okay, so it tells me that I have 9 electrons. I can have 2 electrons in the first ring. Well, if it has a total of 9 electrons, that means I have 7 more to go because I've already placed 2. So I'll just put 1, 2, 3, 4, 5, 6, 7. Try to evenly distribute them around the second ring as best you can. All right, so that's a total of 9 electrons. 7 in the second ring and 2 in the first. So this has what I would consider 7 valence electrons. All of the electrons in the outermost shell are valence. Okay, so if you look over here, fluorine, I have written above it 7 valence electrons. Okay, well, in order to complete the octet rule in the second ring or shell, I need 8. So that means that fluorine is missing 1 valence electron. Okay. So it needs 8, it has 7, it needs 1. Well, it just so happens that lithium has 1 valence electron. So ionic bonding occurs when an element gives or takes valence electrons from another element to complete the octet rule. So lithium doesn't have a complete octet rule. Fluorine doesn't have a complete octet rule. Well, what if lithium says, hey, I'll give you my valence electron. So what's going to happen is lithium is going to give away its 1 valence electron, gives, to complete the octet of fluorine. So if lithium gives away that 1 valence electron, to fluorine, fluorine now has a total of 8 valence electrons. It had the 7 and it got 1 from lithium. So now it has completed its octet rule. It now has 8 valence electrons. Yay! Well, lithium up here also benefits. What happens is when lithium gave away its valence electron, this entire ring went away. And below it, you now have 2 electrons in the lower ring. And even though it's the number 2, it still has completed its octet rule because you can only have 2 electrons in the first ring anyway, so that's perfect. So after lithium gives away its valence electrons, it's now going to look like this. So it has 3 protons and only 2 electrons. So that entire energy level or shell goes away because it gave away the electron. It now has 1, 2 electrons in its outermost ring, its new outermost ring. And that completes the octet rule because you can have only 2 electrons in that ring. So it's perfect. So I know the word octet means 8, but in this situation, you could also think of it as a duet rule. So I'll say duet meaning 2 or octet rule meaning 8. Okay. So down here, fluorine still has 9 protons and 9 neutrons. Neutrons don't really matter for this conversation. And it took an electron from lithium. So it now has, instead of 9, it now has 10 electrons because it gathered that extra electron. When this happens, when you end up with an unequal number of protons and electrons, it is called an ion. Ionic bonding. So this is the ion form of fluorine, and this is the ion form of lithium because it has 1 less electron here. We denote that with a special symbol. So when lithium is an atom, lithium is an atom. I'm going to leave off neutrons. It has 3 protons and 3 electrons. It gives away its electron. When that happens, it becomes an ion. 3 protons. It gave away an electron, so it now has 1 less electron. And here's the thing. If it has 3 protons, it has 3 positive charges. If it now only has 2 electrons, it only has 2 negative charges. So that means it ends up with 1 extra positive charge. So the ion is denoted as lithium plus 1 because it has 1 extra positive charge. Here, you had 3 protons and 3 electrons, and they canceled out. So there is no charge here. This is written as what is called a superscript, meaning you write it up and to the right. Same thing here, 9 protons, 9 electrons, those cancel out, so there is no superscript here. But here we have 9 positives and 10 negatives. So the ion, fluorine, is going to have 1 extra negative charge, -1. That's the why behind this. All right,